Thanks for joining, guys. I hope you enjoy the video.
Coming at you live from the Gordon H. Show right outside RIT's Tribology Lab. My name is Stoyanovich. I'm a third-year mechanical engineering major, and I'm part of the McNair Scholars Program for the RIT Research Symposium of July 2020. I'm working under Dr. Patricia Iglesias Victoria for the Mechanical Engineering Department, Kate Gleason, College of Engineering. My project is the low-cost, environmentally friendly Protic Ionic Liquids as lubricants and lubricant additives. And I'll see you right in the lab.
So here I'm taking you in the daily life of an undergraduate RIT student working in the Tribology lab. Here you'll see the equipment that we use, different tests that we're running, the different lubricants, and I'm using aluminum and steel contact. But we'll explain that a little further for now. So this is just to give you guys an idea of what the lab looks like. Alrighty. So, as you guys know, my name is Stoyanovich, and this is my presentation. We'll get started. We'll break into 5 subsections. We'll go introduction, research questions, methods and materials, results, and lastly, conclusions. So first, tribology. It is estimated that 17% of the world's energy consumption is resulted from frictional losses. These losses are found in the wear and tear of machinery and components that end up needing replacement. With better maintenance and lubricants, a significant portion of the world's energy consumed will decrease. And tribology is the study of frictional losses, wear, and lubrication between surfaces. Through tribological advancements, we can make a greener world. Alrighty, friction. So friction is the ability to resist motion, and frictional forces are present between 2 contacting surfaces. It's why you can go faster on ice skates than you can on just normal roller skates. Wear is the removal of material as a result of frictional forces. So like sandpaper on a 2x4 or using the abrasive side of a sponge to clean the dishes. Wear is found in natural parts of the world, like in mountaintops, cliffs, and valleys, up until the things that we use on a day-to-day basis, like gearboxes and even in our cars. And so how do we stop wear loss around the world? With lubricants. Lubricants contain a type of base oil, either mineral, synthetic, or vegetable. And the reason lubricants are so important is because they allow machines to have longer lasting lives, be more efficient, more reliable, and have less parts to replace and purchase. Lubricants can also reduce heat. It's why when you rub your hands really fast, you can see you get to a really high temperature. But then if you were to put some either water or soap in between, it would take a lot more of an effort to get to that same temperature for your hands. So what lubricants are we going to use? Ionic liquids. Ionic liquids are used as lubricants because of their excellent physical and chemical properties. They're non-flammable, they have thermal stability, no vapor pressure, meaning they're not very reactive. And ionic liquids are also environmentally friendly, unlike their petroleum-based counterparts. There is one distinction we need to make within the realm of ionic liquids, and that is aprotic versus protic ionic liquids. They both share anions and cations that push away from each other, forming a lubricating surface. However, protic ionic liquids are easier to synthesize, meaning lower cost, and non-toxic, while aprotic have a more complex synthesis route and can even form toxic acids if exposed to moisture. So, the research questions. Can low-cost, environmentally friendly Protic Ionic Liquids be synthesized in our lab? And can Protic Ionic Liquids be used as additives to a base oil to effectively reduce friction and wear of aluminum steel contact? You'll see with our methods and materials. So here's a practical example of an aluminum 8-cylinder engine made by Chevy. The reason why this is so important to us is because the pistons that are used for this engine are made of steel. And so over time, as we discussed with wear, we know that over time, the engine is going to be subject to frictional forces and frictional losses. And so if we can find lubricants that prevent this from happening over time, we'll be in really good shape. Aluminum and steel are very popular in the industry, and steel is used because of its high strength, efficient and modifiable properties, and aluminum is used because of its low densities, lightweight, resistance to corrosion, and its thermal and electrical conductivities. Aluminum is also the world's most popular metal. And so how can we test aluminum steel contact in the lab? With our tribometer. So here we have a pin with a steel ball, which is resting on the top of this aluminum disc. The aluminum disc is going to have a wear track where over time the steel ball will rub against it for the course of an hour. The steel ball will also have a wear track on it, but what we are looking specifically at is what happens to this aluminum disc over time. So here we have the tribometer at work. You can see that the stage here oscillates back and forth, and there's the lubricant in between the pin and the pin with the steel ball and the aluminum disc. And as you can see here, this red string over here is our strain gauge. That gives us a live feedback for our coefficient of friction over the course of that whole hour. So over time, we'll see, we'll use these different lubricants. Here we have the base oil and base oil with additives that's commercially available by the company Repsol. It's a Spanish company. And thanks to them, they provided us with base oils to go by. We added a 1% weight concentration of these three lubricants, 1% ETS to the base oil. We did a 1% MTS to the base oil and a 1% weight concentration of DTS to this base oil to get results. Here are the molecular structures of ETS, MTS, and DTS. And these are some of the other lubricants we continue to plan on testing. So here we have our viscometer, our ultrasonic processor, and I'll just run through quickly each of the devices that we'll be using. We'll use the optical microscope to analyze the wear track on the pin and ball. And we'll use the Olympus optical microscope to look at the wear track of the aluminum discs. So now we can look at our results. So after our test, after looking at our 3 Newton load, we had the same stroke length and frequency for all of our tests, and they were run for an hour. We noticed some astounding results. With only a 1% weight concentration of these 3 lubricants, we saw almost a 40% reduction in a friction coefficient. This is huge because this was only a 1% weight concentration. Imagine if we added maybe a 2% or a 3%. That would reduce wear and friction across the board with many applications. And so here we also, for wear volume, we noticed that the largest difference was with our ETS, which had almost a 16% wear reduction, which is pretty good for just an hour. Think about the machines that are used to build cars. They're working constantly all day long. And so we can make a significant difference if we implement these environmentally friendly lubricants. And looking at the wear tracks, here we have this our typical our base oil wear track. And then you can see here's our ETS. You can see there's more yellow on the top of this. So we had a little bit of a narrower track. And you can also see the abrasive marks that were made in these zoomed up images here. For our optical microscope, this was the one that we used to look at the pin, and we have it zoomed into, this is the ball. We see that this is the ball before the test when it's cleaned. This is the wear track for the base oil, with additives. These were both by Repsol. And then these were some of our great examples of our MTS and ETS wear tracks. And we'll get a closer look with this picture here. So you can see here the base oil left a pretty, I guess, noticeable mark, you could say. But here for our ETS, just our 1% weight concentration, we can almost not even see the wear track that's happening in the middle of our figure. And so that's a pretty astounding result. And this is just on the ball. Now let's look at our conclusions. So to conclude, we synthesized 3 environmentally friendly Protic Ionic Liquids and used a 1% weight concentration as additives to commercial base oils. Both 1% ETS and 1% MTS had an incredible anti-wear performance. And MTS yielded the smallest coefficient of friction with a 39.6% reduction. The wear tracks created by the 1% ETS were significantly more narrow than that of commercial base oils, which leads us to wondering about our future plans. We will do several viscosity tests for each tested lubricant, including viscosity tests of the base oil and the base oil with additives from Repsol. And we would also like to add an ETS concentration to the base oil with additives that is commercially available to see if we can yield synergetic effects in terms of coefficient of friction and wear. And reflecting back, we see that 1% weight concentration of these additives demonstrated a significant change in the efficiency of wear mechanics, but we also need to account for human error. The fluid might not always be properly distributed, and then the question lies, what would having maybe a 2% weight concentration of a Protic Ionic liquid with a base oil, how would that impact a ball and disc for aluminum steel contacts in the future? Alrighty, and so here's to our special thanks. Thank you guys for joining me for this presentation, and a huge thanks to the LSAMP and McNair program for not only helping me fund my research, but also give me assistance every step along the way, especially in these very difficult times. Thank you, Kate Torrey, Joanna Victor, for the LSAMP and McNair programs. The Repsol, the Spanish company that provided us with those base oils, Dr. Iglesias, my mentor, Hong Guo and Junru Pang, my lab mates, and Jan Minetti for departmental access, and of course the Stoyanovich family for helping make research in Rochester, New York possible this unique summer of 2020. Thank you guys.